So welcome everyone to this very interesting webinar on adaptive finite element methods by Professor Majid Nazem from RMIT University in Melbourne, Australia. Before we get to the webinar, I would like to just welcome you all back from after the break. So we are back to business now, and we have a lot of really interesting webinars, including this one here today, scheduled for the coming weeks and months. So it's a fortnightly event, and here are some of the scheduled scheduled speakers until the end of November. We have the usual system of the speaker giving the webinar. It's going to be, I think, about 40-45 minutes, and then we will have a Q&A session to conclude. You're very welcome during the talk to type in questions in the Q&A field. If you press the Q&A button there, you should have a window open, and you can then type in some questions there. Majid has also promised that he will take personal questions. So if any of you have questions that you would like to ask in person after the webinar, please raise your hand and then I will unmute you. So with that, I think we should get to the webinar. So over to you, Majid, and you share your screen.
Okay, thank you, Christian. I think you need to stop sharing your screen so I can start mine.
Well, okay, sorry about that.
No, that's all right. Cheers. Okay, do you see my screen?
We see your screen, yes.
Okay, fantastic.
We don't see your camera though, Majid. I don't know if that's deliberate. But...
now I can turn it on.
Here we go. Yes.
Okay.
Thanks.
Okay, please let me begin by acknowledgement of the country. RMIT University acknowledges the people of the Woiwurrung and Boonwurrung language groups of the Eastern Kulin Nation on whose unceded lands we conduct the business of the university. RMIT respectfully acknowledges their ancestors and elders, past and present. RMIT also acknowledges the traditional custodians and their ancestors of the lands and waters across Australia where we conduct our business. I would also like to begin my presentation by thanking the organizers of this webinar, the University of Liverpool, Professor Christian Krabbenhoff, and Optum Computational Engineering. I'm honored to be here. Okay, my university, RMIT University, has 3 campuses in Melbourne, 2 campuses in Vietnam, and 1 in Spain. And based on QS World University rankings, RMIT Engineering is ranked 141st in the world and 9th in Australia, and its civil engineering discipline is amongst the top 100 disciplines. As you know, Melbourne is the capital city of Victoria, located southeast of Australia. This is a snapshot of Federation Square and its typical atmosphere in normal conditions. And those of you who have visited Melbourne before perhaps remember this place. However, recent lockdown due to COVID has had a big impact on us. And this photo was taken a couple of weeks ago around 7:40 p.m. And this is the Flinders Street station, just opposite Federation Square in previous photo. Anyway, about this presentation, today I will talk about adaptive finite element methods, but will mainly focus on the work done by myself, some of my previous postgraduate students, and my colleagues at the University of Newcastle and some at RMIT. I will also discuss the application of adaptive methods in geotechnical engineering, whereas the concepts explained here are multidisciplinary and can be applied to a wide range of problems in computational mechanics. I also acknowledge that the research conducted on adaptivity is relatively extensive, and I may not be able to mention many international or domestic contributors' names in my short presentation today, and therefore I apologize in advance. Okay, geotechnical engineering problems in view of computational mechanics are pretty difficult to tackle. We basically deal with a very dynamic environment called nature. The soil can be totally dry, or it can be fully saturated, including two phases of solid and liquid, or it can be unsaturated or partially saturated, including three phases. On the other hand, these phases are interchangeable. For instance, rainfall may trigger a landslide. Also, there is diversity in size of particles. For instance, compare a clay soil with big rocks. Anyway, unlike many engineered materials such as steel or reinforced concrete, we don't have any standard factory controls over the material we deal with. Okay, why adaptivity? With this complex nature in mind, let's see why we need adaptivity. So first reason is to obtain a solution with a controlled accuracy, but taking into account the computational time. So for instance, you may solve a problem with a uniform mesh and a dense mesh to find a relatively exact solution, or you may start with a coarse mesh and then increase the mesh density where required and obtain the same, more or less the same answer, but at a lower computational time or computational cost, if you like. In some cases, we use adaptivity just to obtain a solution. This is mainly the case with problems with relatively large deformations, and I promise you that I will show you a few examples of these problems during this presentation. Okay, adaptive methods, there are mainly three adaptive strategies: P, H, and R, and of course their potential or their possible combinations. P is when you improve the accuracy of your solution by changing the order of interpolation functions. H is when you start with a coarse mesh and then increase the mesh density during the analysis. R is when you start with a relatively fine mesh, but keep refining the nodal location or the position of nodal locations without changing their numbers or the elements connectivity. So basically you keep the topology constants during the analysis. Or you may have a combination of them, for instance, HP adaptivity or RH adaptivity. Well, in this presentation, I will mainly focus on H, R, and their combination, RH adaptivity. Okay, H adaptivity. So in this method, we start with an initial mesh, and then we normally, in nonlinear problems, we do incremental analysis, and we keep remeshing based on some error in the mesh, and until we find we get to the final solution. R adaptivity is when you don't really change the topology, the elements and their connectivities. For instance, let's say you have a mesh at time t, and then you solve it for the increments, and then your mesh at time t plus delta t tends to be a little bit distorted. So with this in mind, and before starting the next increment, you refine the mesh, but the number of elements and the number of nodes remain unchanged. Perhaps you have heard about this method called arbitrary Lagrangian Eulerian. In this method, there are two types of displacements, grid displacements and material displacements. And the analysis in this method can be conducted in a coupled form, where the grid and material displacements are present in the global equations, or it can be decoupled, where we basically decouple or separate the grid displacements and material displacements. Well, decoupled ALE is referred to as operator split technique, and this method is classified as R adaptivity. Unfortunately, in some literatures, the H adaptive finite element method is classified as ALE, but I need to emphasize that ALE is not equal to H adaptivity, but falls within the R adaptive finite element methods. Now we can combine RH adaptivity to take advantage of H adaptive as well as R adaptive techniques. So in RH adaptive strategy, we start with the coarse mesh, and then during the analysis or during the increments, we may generate a new mesh or refine the mesh. So both are possible. Okay, there are several ways to set up the RH adaptive algorithm, and this is what we have considered in our research. So red color denotes the path of H adaptivity, whereas the green represents the R adaptivity, and black is basically shared between both. So we start by generating a relatively coarse mesh, and as you can see, we are conducting an incremental analysis. So on the right, this is the main loop over the increments. So for each increment, we follow a procedure, and then we check if we have reached the last increment or not. If yes, we stop. Otherwise, we increase the increment and then go to next increment. Now, inside each increment, first we can check if H adaptivity flag is on. If yes, we follow the H adaptive procedure. If not, we follow the R adaptive procedure. In H adaptive, we first estimate the error. If the error is acceptable, we go back to we switch back to our R adaptivity. But if the error is not acceptable, then we need to calculate the new size of elements, or we need to basically work out a new mesh density, generate a new mesh, and then go to mapping procedure. If we have followed the R adaptivity, we do mesh refinement without changing the topology of the problem. Again, we go back to the mapping procedure, and after mapping the procedure, we need to make sure that the equilibrium and plasticity consistency condition are satisfied, and then go to the next increment. Now, as you can see from in this algorithm, there are several main ingredients in our adaptive finite element techniques: generating a mesh, estimating the error, refining the mesh, and mapping procedure. So keep these three main ingredients in mind, and I will explain them briefly during this presentation. I start by error estimators, introducing only 3 error estimators here, and then I will compare their performance later by some numerical examples. While these error estimators are energy norm, Green-Lagrange strain, and are based on Green-Lagrange strain, or based on plastic dissipation. So H superscript on this slide basically represents the variable calculated by the finite element at the Gauss point or integration point, whereas an asterisk superscript denotes its smooth value over the element domain. And of course, EL stands for element. So these are the errors in an element. If we want to work out the error in the entire domain, we just replace the volume of the element by the volume of domain. Energy norm takes advantage of the true stress sigma or the Cauchy stress, as well as the linear strain. Green Lagrange strain includes a linear term, like a simple strain, as well as a nonlinear term for a nonlinear term. The plastic dissipation, very similar to energy norm, but the difference is here that we use the incremental plastic strains rather than the total strain for working out the plastic dissipation. Okay, mesh generation and mesh refinement are another important ingredient of adaptive methods. I'm not going to talk about the mesh generation methods here because they are well established in the literature. And even if I talk about them, perhaps for 2D problems, I will suggest just using either advanced front method or just use Delaunay triangulation. But with regard to mesh refinement and what it means, so let's say we have a mesh at time t at the start of a new increment, and then we solve the increments, we find the displacements, and we update the nodal displacements as we normally do in an updated Lagrangian analysis. Now, this mesh tends to be distorted, or if we don't really do something here in this increment, it may get distorted during next increment. So we need to refine the mesh. What do I mean by refine the mesh? So first, as you see here, we forget about internal nodes, but we just relocate the nodes along the boundaries. Boundaries can be external boundaries or boundaries between two materials. After doing this relocation, next step is to relocate the internal nodes. So now we do the relocation for internal nodes, and we end up with this mesh at the end of the time increment. And we will use this mesh for starting the new increment. So this is a simple explanation of the mesh refinement. Now, in terms of relocation along boundaries, we need some functions to represent those boundaries. And if you look at the literature, people have used linear functions, quadratic splines, B-splines, even radial basis functions for just representing those boundaries, and then taking care of the relocation of nodes along them. Relocation of internal nodes, these methods are also very popular: elastic analysis, spring analogy method, RBF interpolation method, elastic hardening method, and reference Jacobian method. Unfortunately, I don't really have time to go through these methods, but one of my former PhD students devoted a couple of his PhD chapters to these methods, and you can refer to that PhD thesis if you are interested. Okay, after generating a new mesh or refining a mesh, we need to remap variables, state variables, and also the nodal variables from the old mesh to the new mesh. Now we need to consider nodal points, variables stored at nodal points, for instance, displacements, velocities, accelerations. And these can be easily done by using the interpolation or shape functions. But for integration points, it's a bit complicated. So here is how we can do this remapping in H adaptivity. So this is our old mesh, includes 4 triangular elements. This element and this element have been divided into 2 sub-elements in the new mesh. So as you can see, our new mesh includes some new Gauss points, and we need to work out the values of state variables such as stresses, strains, and other variables at this new Gauss point. So how do we do that? In our old mesh, first we consider a patch. So for this red node here, I have shown the patch, as you can see, and then we map all the variables from Gauss points in this patch to this node. And then this node exists in our new mesh, So we can then map again the state variables from this node to new Gauss points. For if we are doing our adaptivity, the procedure is more or less the same. So this is our mesh at time t. This is our refined mesh. As you can see, the location of these Gauss points have changed after refinement. Here we can use this. This is called convection equation in the ALE literature, but it's basically the linear expansion of Taylor's function, of Taylor's series for a function. So for any function f, the new variables are basically its old values in the old mesh plus the gradient of that function and times this is the velocity of material points. This is the velocity of mesh points. Basically, the change between the coordinates of these Gauss points. So after we do the remapping, now we need to check the global equations again. If we are solving equilibrium, we need to make sure equilibrium is satisfied in this new mesh. If you have any stress points previously in the old mesh on the yield surfaces, these stress points may be located outside the yield surfaces after remapping. So we need to make sure that we bring those points back on the yield surface and make sure that plasticity consistency is not violated. Okay, some applications. I'll show you some applications: footing problems, penetration problems, and dynamic compaction, depending on how we go with the time. This is a strip footing over a cohesive soil layer. The shear strength of the soil is SU, and its shear modulus is G. The main aim of this problem is to show you the performance of error estimators when this problem is analyzed, assuming small or large deformations, and also considering static or dynamic loading. With a small deformation, we know the exact solution, exact plasticity solution. It's called Prandtl plasticity solution. And of course, the bearing capacity of soil under this strip footing is obtained by 2 plus pi times its shear strength, which is 5.14 times SU. We use 3 different error estimators for conducting our RH adaptivity here: energy norm, green Lagrange strain, and plastic dissipation. Based on each energy norm, we could work out the bearing capacity, so you can see the obtained answers and the number of nodes at the end of analysis, how many nodes we ended up to have at the end of the analysis. Also, the CPU time, it's a normalized CPU time of each analysis. And of course, for this case, as you can see, plastic dissipation outperforms the other 2. Now, I have solved this problem, again, assuming a small deformation, but conducting a dynamic analysis. So for dynamic analysis, the pressure of the footing of 10 SU is applied on the footing over 1 second. So we have the settle. I haven't actually shown the deformed, the meshes at the end of the analysis, just to give you a few seconds to think about it and see if you can guess how they would look like. It's very interesting. So settlements obtained under this load by energy norm, by green Lagrange strain, as error estimator, as well as plastic dissipation. In this case, we have the number of nodes at the end of analysis and the CPU time, the normalized CPU time. So if you have guessed the pattern, the final meshes, let's see if you're right. And this is how those meshes will look like at the end of analysis. And the first time I saw this one, I thought about the Darth Vader face from Star Wars, actually. Okay, now doing the same problem, dynamic analysis, large deformation. For dynamic analysis, we solve this equation, and again, this load, the normal pressure of 10 SU is applied on the footing over 1 second, and we have the final settlements predicted by these 3 error estimators, as well as number of nodes at the end of the analysis. Again, for dynamic large deformation, the Green-Lagrange strain tensor has outperformed the other 2. In previous example, I didn't show you the results of static analysis, but assuming large deformations. But I'm now showing you the results using the R-adaptive finite element method. And in this case, the materials are more or less the same. It's a Tresca material with undrained shear strength, but footing is pushed down inside the soil, and the displacements are extremely large. Here we have the displacement normalized by the total width on the horizontal axis, and the pressure on the footing normalized by its undrained shear strength on the vertical axis. So if you remember, for simple, for static small deformation analysis, this pressure is 5.2 plus pi times SU. So that's the plasticity solution assuming small deformations, whereas when we turn the large deformation flag on, the results are a bit different, and actually the predicted plots depend on this ratio, which is the rigidity index of the soil. G shear modulus, SU, it's on undrained shear strength. Okay, another example here is a cone penetration. Again, a static as well as dynamic analysis. The soil is cohesive and frictional. So these are the results of the static analysis using RH adaptivity. In each analysis, the maximum of value of an element area in the initial mesh is set to 1.2 d squared, d being the diameter of this penetrometer. This represents a relatively coarse mesh at the beginning. During the adaptive analysis, this the minimum area is set to is limited to 0.02 d squared. Now, you can see the meshes at the end of each analysis by energy norm, plastic dissipation, and Green-Lagrange strain. More or less similar meshes, but the time and the degrees of freedom are a bit different. So here we have the growth in the number of degrees of freedom versus analysis time for each of these methods: Green-Lagrange strain, plastic dissipation, as well as energy norm. And here again, my money is basically on the Green-Lagrange strain error estimator. We have solved the same problem, but just done dynamic analysis. For dynamic analysis, the error estimators based on plastic dissipation and energy norm could not finish the analysis, whereas Green-Lagrange strain tensor error estimator was successful in completing the analysis. Okay. Now I'm going to present the application of R adaptivity in dynamic penetration problems. These problems have many applications. It could be a small bullet penetrating into a life vest, or missiles penetrating into civil infrastructure, or in larger scales, it can be a torpedo anchor penetrating into ocean bed in order to anchor a floating oil rig. I will mainly address this problem and the torpedo anchor here These are the research areas that I have recently started, but I don't have really any results for these problems, but will mainly focus on torpedoes and penetrometers, the free-falling penetrometers. Okay, what are the main characteristics of these problems? Basically, the soil behavior is highly nonlinear. Deformations are relatively large. We need to consider contact mechanics due to changing boundary interface, changing interface between the torpedo and the soil. Some cases, in torpedo case, we have a two-phase medium. Of course, the problems are time dependent, and we also need to consider the presence of inertial forces. We can do this kind of analysis in two forms. One is just use the standard displacement analysis and conduct the analysis in terms of the total stresses, or we can do a coupled displacement for water pressure analysis, and I will go through both of them shortly. In undrained analysis, we solve for the dynamic equilibrium equation. Soil behavior can be expressed by Tresca material, and we should consider the increase in shear strength due to strain rate effects. And one possible equation is this one, and lambda in this equation is called the rate parameter. We also need to consider the shear strength increase due to depth, due to increase in depth, and this is usually, we can assume, a linear function for shear strength increase. Before doing torpedoes, we have compared our numerical results with some experimental results. So these tests were conducted by my colleagues at the University of Sydney. So basically, they dropped some free-falling penetrometers onto a layer of soil. So we have measured penetrations in lab, and we have predicted penetrations by the finite element method, or our adaptive technique here. And the difference in these cases, difference between the measured and predicted penetrations change between 1.4% up to maximum 25%. In overall, we were quite happy with our numerical method, and we basically took care of its validation. Now, I'm gonna show you the results of four torpedo anchor simulations using undrained analysis. So a bit bigger, diameter is 1 meter, mass is around 10 tons, impact velocity of 10 meter per second. These are the soil parameters, and these are the predicted total depth of penetration predicted by the R-adaptive method, as well as the total time of penetration in seconds. So as you can see, for instance, for case one, the rate parameter 0.25, the shear modulus of 67, and then this is the rate of shear strength increase with depth. The total embedment depth is around 10 meter, and it takes 1.26 seconds for the torpedo to stop. This is the variation of velocity versus time. So at the beginning of penetration, the torpedo is still accelerating. As you can see, the velocity increases rather than decrease. And this is mainly due to the fact that torpedo is accelerating under its under gravity, and the weight is basically larger than the soil resistance during this acceleration. But after that, you can see that torpedo starts to decelerate until its velocity goes to 0. This plot suggests that the velocity versus time is kind of quadratic. We have velocity, normalized velocity versus the total penetration. Really large penetrations followed by large deformations as you can see in this plot. So these are some typical results from undrained analysis. Now we can do a coupled UP analysis. So in this kind of analysis, we need to consider the mixture momentum, power fluid momentum, conservation of mass, and the principle of the effective stresses, because we are dealing with the two-phase medium. U stands for the displacements. So U dot and U double dot will be velocities and accelerations. P is the pore water pressure. Now, we should note that in this case, we can't use terrestrial soil model anymore, because the considered metrics in stiffness matrix needs to be defined in terms of the effective stresses in this case. One example of installation of torpedo, the length is 6 meter, diameter is 0.6 meter, 3 different impact velocities of 10, 15, and 20 meter per second. And the weight is 40 Newton. We used modified camp clay soil model in this simulation with these parameters. Again, we have the plots of velocity versus time, as well as velocity versus penetration. The trends are very similar to what we saw in previous example. And this is a typical soil resistance during the penetration. I think this is for the case where the impact velocity was 15 meter per second. So with a modified camp clay soil model, the Undrained shear strength soil resistance in this case is a function of effective stresses, and effective stresses change linearly with the depth. So you can expect a linear soil resistance during the penetration. And the time scale here is not 100% correct. The video is perhaps 4 to 5 seconds, whereas the torpedo in numerical simulation stopped at perhaps within 1 second or so. Well, this is how it looks at the end of simulation. Okay, the UP analysis, or the coupled analysis, enable us to have a look at the excess pore water pressures during the installation. So this is the plot of excess pore water pressure when the torpedo is at 5D penetration. D is the diameter, and this is a similar plot when the torpedo is at 11D of penetration. So these figures show that a compressive excess pore water pressure bulb grows around the anchor tip and shaft during installation. Well, in terms of dimensions, this bulb extends a distance of approximately 2.5 D in the radial direction and about 1 D in the vertical direction below the tip of the anchor. In addition, we have a tensile region located about 1D vertically under the anchor tip, and there's another region with similar specifications located just below the ground surface. Okay, and the last application is about dynamic compaction using R adaptivity. Now, dynamic compaction is a method used for improving this load-bearing capacity of soil, for instance, for building a new harbor. Relatively big and heavy weights, or pounders, if you like, are lifted, and then they are dropped onto the soil, this can basically densify the soil. So in terms of the size, if you look closely, that red point is a person standing just next to one of the footprints of this pounder after impact. Now, there are several questions, interesting questions in this problem. For instance, what's the depth of improvement of the soil? Or how many drops are required to achieve a certain improvement in soil parameters? And so on. So of course, I'm not in a place to answer all those kind of questions today, but least I can do is just to show you an example. So we have a pounder with the diameter of 2 meters, and the mass is 10 tons. And this is the finite element mesh used in this example. I don't have the time to discuss the soil model used in this study, but of course you can refer to this paper if you are interested to know about the soil model. Several analyses with different energy levels from 120 kilonewton meter up to, I think, 720, and there was another one at 840, but is not shown on this plot. So the settlement of this pounder definitely depends on the energy level, and in some cases this can be relatively large displacement or settlement. Yeah, this is a comparison between the R-adaptive method and the updated Lagrangian. Of course, this shows that you definitely need an adaptivity technique to solve this problem. So this is for the energy of 845 kilonewton meter, and it's this is when the impact velocity of the pounder was around 13 meters per second, which means the pounder is released from around 8.5 meters above the ground surface. And the final settlement is around 1 meter or 1 radius of the pounder. These plots show how the void ratio changed due to dynamic compaction for dropping a 10-ton pounder from 2.5 meter height. On the left, you see the change of the void ratio versus change of void ratio versus depth for different values of lambda. And lambda on this plot is not really the rate parameter, but it's the slope of the normal consolidation line in the modified Campbell soil model. Here also on the right, you see the same, more or less, same changes or same pattern with, versus depth for different values of kappa. And kappa is the slope of URL unloading, reloading line in the modified Campbell soil model. So significant observation is that, as you can see, the majority of soil improvement, or let's say densification or changes in void ratio occurs just 2 meters up to 2 meters below the ground surface. And surprisingly, 2 meters is the diameter of the pounder. There are some changes between 2 and 4 meters, but after 4 meters, basically you can't observe any significant changes in the void ratio. So I hope I was able to introduce you to the application of adaptive finite element methods in computational geomechanics. In my humble view, these methods are relatively mature, but they still demand more research. For instance, 3D applications or parallelization. I would also like to, at the end, I would like to acknowledge Australian Research Council through a Discovery Project scheme, and also the ARC Centre of Excellence for Geotechnical Science and Engineering funded by the Australian government. I also acknowledge some of former PhD students who have worked on this problem, and also some of my colleagues with whom I have been collaborating for the last perhaps 10, 15 years. And once again, thank you for the University of Liverpool and my dear friend, Professor Krabenhoft, for letting me to present this webinar. Thank you for your attention.
Thank you very much, Majid, and thank you for presenting. It was really interesting. We have some questions.
Sure.
Maybe I will. There was a mention some times, some CPU times during the presentation, and there was a bit of confusion as to what the units of those times were.
Yeah. Well, those are basically the normalized CPU times. So what we do, because you know, the technology is changing every day, and the speed of CPUs change very rapidly. So what we have done, we basically measure all computational times, let's say, for instance, in terms of second, and then we divide all computational times by the largest.
Okay, great.
Or sorry, by the smallest. By the smallest in this case.
Sure.
Yeah. So the fastest provides the least time, the fastest method, basically. So let's say, in this case, if the CPU time of Green-Lagrange strain error estimator was 1, energy norm was 3.6. Now, if this one is 1 hour, then energy norm is 3.6 hours. And this one is 2.8 hours. If this is 1 day, that will be 3.6 days, and so on. So basically, it's the measured time divided by the fastest analysis.
Sure. Thanks. Just a more general question, Majid. As you say, these methods are fairly mature now. I mean, it's been done sort of, from what I see, with a few exceptions, is mostly in the academic community. And I was wondering, what is really the price to pay for using mesh adaptivity? Because generating a mesh based on some error estimator is relatively cheap compared to solving the equations. So you would think it would be sort of just a standard technique that everyone would use. But so what are really the complications in it? Why isn't it just completely the default option when you use finite element software to have adaptivity included?
So you mean why not generate a new mesh every time?
Yeah.
If I understand your question correctly.
Yeah. I mean, what I'm asking is, why isn't this technique more used than seems to be the case? And my guess would be because the mesh generation itself is relatively cheap, especially in 2D. There's lots of routines out there for doing this, and even in 3D it's not too bad. So I guess, I mean, one of the main complications is the mapping, if I'm not mistaken, the mapping of your variables from one mesh to the next, which is not really that difficult either, but which may generate some error.
Yeah, I mean, that's one of the complexities. I think, well, you and I have seen many applications of H adaptivity and remeshing techniques in the literature. One area that I think makes this more complicated is where you are dealing with contact mechanics problems, especially when you have an interface or changing boundary conditions between an object, a penetrometer or a structure, and then the soil. So with my experience, when you have that contact mechanics involved in your in your problem, then it becomes even more complicated. And sometimes you have contact, you do remeshing, you remap the variables, no problem, but then you can't really satisfy equation and plasticity condition at the end. And then if you can't do this, then you have to carry these unbalanced forces into your next increment. And these unbalanced forces keep accumulating. And then at some stage, your analysis basically fails or just diverges from the right solution. That's my experience, but I could be wrong.
Yeah. No, this is a good point. Just out of curiosity, when you had the penetrometers there, those meshes with the penetrometers, especially the dynamic ones, you had these kinds of mesh concentration, you could say. Yeah, maybe this one. You have these small areas there along the pile where you seem to have a really dense mesh. Is that a coincidence, or is it just the way it is with the energy norm, with whatever norm, that error estimator that you use?
I think it is what it is. I have no explanation for that.
Sure. Okay. There is a question: how general is this methodology in terms of the material model that can be applied? So there's a user that's or a person who's interested in I believe, rock mechanics application, where you would have maybe some anisotropy and so on. But I guess this is relatively independent of the material model.
Yes, these methods are really independent of the material. So because when it comes to material modeling, all you need to know how to relate the stresses to strains at the Gauss point, at an integration point, basically. And but the rest remains more or less the same. So if you tell me how to define the properties of a material or the behavior of a material at the Gauss point, then no worries. You can basically run your analysis using either of these techniques.
Yeah. Interesting question here. Which criteria do you use to stop the refinement? I'm thinking of points with singularities. So if you have a singular point, then you would keep on potentially just increasing the mesh density at that point.
So criteria for stopping I didn't get the last bit.
Yeah,
refinement.
Are there any criteria for, like, when you say enough is enough now, so that you avoid? So, for example, if you have a singularity, you would have to, in principle, you could never refine your way out of that somehow. But I guess what saves you is the plasticity. So so for a linear elastic or for an elastic problem, yeah, you would have a problem with singularities, but for as soon as, I mean, that's taken care of by the plasticity, right? So if you think of the edges of a footing, for example, the stresses there are infinite, right? So
yeah,
it's elastic, which it of course isn't.
Well, I think it depends on several things. If you are doing a dynamic analysis, and if you are doing explicit time integration, then you have some limitation on the element size for the stability of your time integration, if it's explicit. fortunately, we have been doing implicit integration, so we had no issue there. What in terms of the size of elements, in our adaptive techniques, we can basically adjust the minimum and the maximum size of elements as an input, and then our code takes care of it. So it won't generate elements larger or smaller than a prescribed value. But I'm also think that your point is correct, especially when it comes to stress integration of the constitutive equations. Yeah.
Have you applied these methods to problems where you have what is commonly known as mesh dependency? So, for example, softening type problems where you have a tendency to a localization of the deformations, and then if you were to adapt there, you would have a very dense mesh around that local, and you could possibly sort of get around, actually, you could kind of regularize the problem in that way.
Yes, we have done that, and I didn't really show it here, but we have simulated biaxial test, and if that's what you mean. So this is one of the very early simulations of this type. This is a biaxial test, but the behavior of this problem really depends on how you define the boundary conditions, of course. But yes, to answer the question, yes, we have applied it to this kind of localization problems.
Okay, yeah.
Yeah.
And then there's a slide 52 and 53 on the dynamic, 53, 54 on the dynamic compaction. Yeah, so the void ratio is the comment. I mean, it compacts until about 2 meters or so, and then there's sort of something happens there at about 2 meters. that it kind of
oh, you mean this little kink here? Is that what you mean?
Yes. Kind of a funny.
Honestly, I have no explanation for this. I can't explain it. Yeah, it's a bit weird, but I don't know the reason behind it.
Okay. By the way, was this problem was carried out in 2D then with axis symmetry, Majid?
Yeah. Yes.
What about these radiation boundary conditions? So when the waves hit the boundary, something happens. Either they're absorbed completely or they're kind of reflected back. And how do you handle that?
I stopped sharing my. Do you still see my screen?
No, it's not.
Sorry. Give me a second. I mean, these problems have so many details that I usually forget to mention all details.
Sure.
Yeah, for instance, for this one, we have energy absorbing boundary, because it's true. In dynamic cases, you have wave propagation, and these waves move toward the boundaries, and if they are just standard finite element boundaries, they will bounce back and they will pollute your numerical simulation. but we use energy absorbing boundaries here and even down the bottom, so it absorbs the oncoming wave and doesn't reflect the reflection. Yeah, we do that. Yeah.
I think we are getting to the top of the hour now, but we'll have one question as well, and it's on the details as well. What kind of numerical and kind of time stepping essentially do you use? Is it implicit or explicit?
Implicit, and almost in all dynamic simulations I showed here, we use the generalized alpha method, which has two integration parameters, because the inertia forces and damping forces are measured at two different times between t and t plus delta t. And it was actually developed by structural dynamics people, but it's been found to be very efficient for geotechnical problems as well. So generalized alpha method, implicit time integration.
Great. Thanks a lot, Majid. Again,
my pleasure.
I think we will end it here, and thanks to all the attendees as well. I'll just try to share my screen.
Sure.
I will do that. Like that. And just as a final reminder here that we'll be back in 2 weeks with another very interesting webinar by Britta Beanen from the University of Western Australia, and that's on the 15th of September. But for today, that's it. And thanks again, Majid, and thanks for attending. And if you just hang on, Majid, then
sure.
We'll just have a chat afterwards. And see you next time.
Thank you, everyone, for your attention.